Yes. All right. As far as homework goes, if you just give me your table, I can pick it up a little bit. This is still actually 4.1 for right now. So I'm sorry, 4.2. We'll finish up 4.2. Then we'll go to 4.3 today. So this right here is still part of 4.2 from yesterday. Homework, guys, just give me your table for now. I can pick it up later. Let's just keep that so you remember to have it. Do you guys need that right now?
It's so I can see my notes.
Oh, can you not see it?
Well, that's difficult. That's dark.
Okay.
Yeah.
Rutherford, we talked about yesterday. Do you remember he discovered? What was his experiment? What did he discover yesterday that we talked about? Yes. Protons, yeah. Yeah, protons, right? So he discovered protons. So based on his discovery, he made a new model of the atom. And this is what he decided, that the atom must have a center, which you can see in red right there. Those are positively charged protons, along with electrons much smaller in size orbiting around. So this is called the planetary model, because he imagined electrons like planets orbiting around the nucleus.
What did he do? So they had no clue neutrons existed.
At this point, no. No, they didn't know.
They just kind of like assume that it was just a proton.
No, they knew that they were missing something. So they could measure the weight of the atom, and they knew there was mass that they could not account for. And so they knew that there was more to it than what they were showing, but they didn't know how to find it at that point. So Rutherford had some problems. He knew this is not the exact right model. He knew that there was things he was missing, but he wasn't sure exactly what he was missing. He just knew that wasn't correct. So what he did say, though, is that atoms are mostly empty space, and that there is a dense region in the center called the nucleus. That's where protons are. And he knew it was very massive compared to the rest of the atom. If you were to make the nucleus the size of the dot in your textbook, it would weigh 28,000 pounds. Not 28,000, 280,000 pounds. So that's a couple of semi-trucks in weight.
Whoa.
So that's how massive the nucleus is in the atom. If you were to make the nucleus the size of the dot in your textbook, that dot would weigh 280,000
How does
pounds.
that work?
That's how massive, that's how dense the nucleus is.
But since then why does it so small? Yeah.
That's
compared
right.
to us, we can't.
Exactly. And that also shows you how much empty space there is in matter.
No joke.
So even the table, feels solid to you, but it's mostly empty space by far, 99.9% empty space. The only reason why it feels solid to you is because the electrons repel the electrons in your hand. And what you feel as solid is just the repulsion of the electrons on the table and on your hand. And it's also solid because light doesn't pass through it. But if you could see it in reality, you would see it's almost all empty space.
So would it be possible to fill that space?
A black hole would be an example of when it's almost all the way filled.
Is that why
So-
they're so is that why they attract, because they're so dense?
Exactly.
Uh,
If you were to make an atom the size of, like the Cowboy Stadium in Arlington, one atom the size of a football stadium, the nucleus would be a paperclip in the center of the field. That's how small the nucleus would be compared to the rest of the atom. And that's how much empty space there is between the nucleus and the electrons. So think of the whole stadium, and that would be the whole atom. The nucleus would be a single paperclip in the center of the field. So it's just hard to even imagine how much empty space there is between the nucleus and the electrons. So this is called the nuclear model or the planetary model. Now, there are several things that he could not account for in this model. He knew that, but it was the best thing he could have at the time.
So if
if the nucleus was as big as a like quarter, how big would an electron be?
Oh, it would be about 2,000 times smaller in size.
Oh, wow. So what would happen if an electron is orbiting and then it hits the nucleus?
Yeah, it can be absorbed by the proton of the electron, or it can just bounce off. It just depends, but it can do one of two things. It can be repelled back off, or it can be absorbed into the particles.
So if it's absorbed, does that change what the atom is?
Yeah, well, it becomes different particles. So you can have different particles arise from that happening.
Can anything just go through the empty space in a solid?
Well, it depends. Like usually no, like you can try, right? You can hit the table, like it's mostly empty space, but you can't go through it, right? Because the electrons in your hand repel the electrons in the table. So generally no, because it's just too much of a repulsive force.
Could
Now,
they make
science-
something that could go through though?
Maybe, we're not sure.
If you took the electrons out of an atom, could it go through?
That would help.
Or if you like charge so if opposites attract,
Yeah.
could you charge it to like attract to the table?
That could help too, yeah.
And then so that your hand is able to go through.
Now, science does say if you were to keep on pressing against the table, eventually you could find a way to pass through it. Eventually your atoms would line up with the table's atoms and you could pass through it, through the empty space. But that would take almost an eternity of pressing against the table for that to happen. So it's not something that's likely to happen, but it's a possibility that it could happen, where you could line up exactly right and go through the empty space. It's
What
just,
about going incredibly fast?
that wouldn't change much
That would
about your
just destroy
chances.
the table.
Right, but
You want to try that?
so it's very, very unlikely, but it is a possibility.
So like kind of like phasing, I guess?
Yeah, exactly. Yes. So Rutherford had two things that were a problem with this model. According to physics, this is not a stable model because he said that he had a negatively charged particle, the electron, orbiting around the nucleus, positively charged. And physics said at the time, if you have a charged particle spinning around, it's not going to become stable. It's going to be like water going down a drain. Water goes down the drain. That's what we see. And it's like he was saying that the water would not go down the drain. You have an open drain, you have water in there, and his model was saying the water would not go down the drain. It doesn't make any sense. That's what happens in physics. So negatively charged particles in motion will spin towards the positively charged nucleus. That's just how it's going to happen. And he cannot explain why they don't do that. So this bottom picture is what physics said should happen in the atom, in which case it wouldn't make sense that they stayed in orbit. He could not explain how these electrons just were like a planet orbiting and not spiraling into the nucleus.
Wait, why does it say positively charged nucleus if that's like an electron?
That's a mistake. I
Or
didn't.
is that what they're saying it will attract?
I guess that's what they mean. I didn't make this make that chart, so I'm not sure what they meant by that. But I guess that is what they're saying. Because yeah, that's the no. I found this online somewhere. The picture I found online. I'm not sure what they meant by that picture, but that is the reverse of what actually those things are. So I don't know what they meant by that. But that's a good thing to point out.
So the blue and red one is Rutherford's model, but the other one is the physics.
Exactly. Yeah, Rutherford said that they should stay in place and orbit around like planets, but physics said no, that couldn't happen.
So what if it's like, the other atoms that are by it, just like planets, pull, like there's a gravitational force from like every single object in the universe,
Mhm.
kind of. What if the other atoms pull on their electron, and so that's why they orbit instead of going to the middle? kind of?
Well, what he would say about that is that the electrons would repel other electrons, right? And so if you have one atom, another atom, what's on the outer shell? Well, it's the electrons, right? And generally electrons repel other electrons. So that would be something that would not help his model. It's a good idea to think about that, but he would say that that wouldn't really be helpful to him. The other thing too, not just that, but because they're charged particles, especially charged particles in motion, become unstable. So it's not just that they were particles in motion, but because they were charged especially, that would just didn't make sense in physics. he also couldn't account for all the mass. And so he knew he was missing particles. He knew that there was something else, which we now know is a neutron. By the time he didn't know that, he knew there was something missing in his model. So those are two problems he had to address. About 8 years later, in 1920, he formally declared that he discovered protons, and he named them protons. So they were a positive component to the atom. In the center of the atom, much more massive than the electrons, about 2,000 times heavier inside and bigger than the electrons. So far they knew about electrons, negatively charged particles moving around the nucleus, and they knew about protons, positively charged particles in the center of the atom. And they set out to find the third part, which they knew existed, but didn't know how to find it. It took about 12 years, but eventually they did find the neutrons. And they used X-ray to crystallization to see the neutrons. And they smashed atoms together, and they saw the effects of that as well. And those two things, X-rays and smashing atoms, led to the discovery of the neutron. And that was James Chadwick, 1932, who discovered the neutron.
Wait, so the 8 years later, like in 1920, that was still,
Yeah, Rutherford discovered he formally named it as a proton in 1920.
and then the other guy, something else.
And then James Chadwick discovered the neutron in 1932. And that completed the model of the atom. At that point, they knew all the parts of the atom. There were three main parts: protons, neutrons, and electrons. And they had a good idea of the structure of the atom. That's just a stopwatch over there beeping. I need to turn those off. The alarms keep on turning back on when I turn them off. I'm not sure why. It's some kind of defect. You go on Amazon, you read the reviews, and they all say they don't stop beeping. We've tried everything to turn them off. They don't ever turn off.
You can
So-
take the batteries out.
I could do that, but then when I use them, I can't use them.
You can
So-
put them back in.
Yeah, that's a pain. Because if you use a screwdriver and like take off two
Oh.
screws and you have to, it's a pain. We already talked about this, so don't write this down again. Let's go through really quickly. An electron is a negatively charged particle. It's a -1 charge. A proton, +1 charge. Neutron, no charge. A proton and a neutron, about the same mass. Now, a neutron is a little bigger in mass than the proton, not by much though. They're about the same mass. And an electron is 1/1840 times smaller than the proton and the neutron. So almost 2,000 times smaller in size. Let's go on to the next section. We're now in 4.3.
Is there an actual ring that looks like that?
No, that's real.
Oh, that'd be sweet.
That's kind of sad.
Sure, it's expensive. So what determines an atom's properties are three things: the number of protons, electrons, and neutrons in the atom. So looking at the periodic table, you can look at a few details for each atom. The top number for gold, it's 79. That top number is the atomic number. And that tells you two things. It tells you how many protons there are and how many electrons. So for gold, it has 79 protons and 79 electrons. The number of electrons always equals the number of protons in a neutral atom. So
What about a magnet?
a magnet is okay, so a magnet has no charge either. A magnet is not charged. You know it's charged if you touch it, it shocks you. And magnets don't shock you, but if it's a charged object and you touch it, you're going to feel a shock. And so neutral objects do not shock you when you touch them, and almost everything that we encounter is neutral.
So is that,
Yeah,
do, Does electric current, do they have more electrons?
Yeah, more electrons.
So that's
Electricity
not-
is just pure electrons. What you see in electricity is just pure electrons in
And
motion.
that's why they shock you?
Exactly.
Can I go to the?
Would friction be like,
Friction can charge objects. So when you like comb your hair, sometimes your hair gets static electricity. What's happening there is the brush is pulling electrons off your hair. Actually, wait, is it the other way around? I forget now. No, yes, your hair becomes positively charged. And so the comb takes electrons off your hair and then makes your hair positively charged and the comb negatively charged. And so if you notice that the comb will stick to your hair, and that's because the comb is negative, your hair is positive at that point. And that's why it attracts the brush or the comb. The balloon on your hair, same exact thing. If you rub a balloon in your hair, the balloon pulls up electrons, makes your hair positive, makes the balloon negative, and you get a charge based on that.
Okay, so I also thought that it was all like force and not that would like if you're brushing your hair, it's not really the electrons, but it's more of like your strength. Oh, I mean, not strength, but like, it's mainly you just like moving on your arm, so I just don't get why the electrons would feel like.
Well, if you're making your hair charged, like if your hair becomes static electricity, like where your hair just like gets, stringy and pulled out, and you can see it's charged. And the more friction you apply, the more force you apply, the more electrons you're pulling off your hair. And so like if you rub your hair faster, you'll get more electrons off your hair and make it more charged. And so that's what's happening if it becomes charged, where your hair actually is flying off and it's static, then you're pulling electrons off your hair to make it charged. Hey, Lillian?
so I've heard like people say that you never like ever really touch anything in your life.
That's true because the reason why we're saying that is that when you hit the table, you are feeling a repulsive force between the atoms in the table and the atoms in your hand. It's like a magnet that repels other magnets. So you actually are hovering above the table. Even if you think you're on the table, there's always a gap between your hand and the table. It's a repulsive force. And so what you feel as solid is really the force of the electrons in the table repelling your hand. And so that is true. You technically never really touch anything.
So is that like kind of a gap in that like you can't see it?
That's right. You can't see it. Well, with a microscope, you can see it, but with your own eyes, you can't see it. It feels like you're touching it because you're feeling the force. That's what you feel as touching something.
So it's like you have a giant magnet.
Yeah, exactly.
How would you like counter in a way, like, like your hair is static or whatever?
Yeah.
How would you make it?
Moisture, water takes away electricity. And so if your hair is really frizzy and you just get a wet comb or wet brush, that is going to help dissipate the charge.
If it takes away electrons, why doesn't your hair become unstable?
Because, well, that's a good question, because the electrons themselves just make it charged, doesn't make it unstable. It just, so if you touch your hair, it's gonna get, you're gonna
So
shock.
if it took away neutrons or protons.
That would be a different story. Electrons themselves, it's still the same atom. It's not gonna become unstable with less electrons. It's just gonna become charged at that point. And also they easily get electrons again. Like, so your hair does not stay charged very long. There's water in the air that will move electrons back to your hair pretty quickly. On a dry day, though, you're more likely to be shocked and more likely to have frizzy hair. Sorry, not frizzy hair, static hair, because there's not much moisture in the air, so the charge stays in your hair for longer. On a humid day, you're not going to get any shocks, because a humid day with all moisture in the air, you're going to have pretty much no charge stay on your body.
So how come when you like the more you pull up electrons, the more it's gonna get charged?
Yeah, because the stronger the force you're applying to your hair, or the longer you're doing that for, the more electrons pull off your hair.
So how come it gets charged if like the electrons are the ones that are like charged, right?
Yeah, so what happens is that if you pull electrons off your hair, and now there's more protons on your hair than there are electrons. So if your hair is not charged, you have the same number of electrons and protons in your hair. If you start to brush your hair and pull off electrons, there might be, let's say you had 100 to start with, you brush your hair and now you have 75 electrons. you have still 100 protons. And so now it's unbalanced. You have more protons than electrons. It becomes positively charged at that point.
So like unbalanced and charged are like synonyms?
Yeah, you could say that as far as normally you have the same number of protons and electrons, right? And so normally they equal each other. As long as it's an equal number of protons and electrons, the overall charge is 0. But if you were to have, say, 25 protons and only 20 electrons, and now you have a charge of +5, right? You know, you have 25 positive, 20 negative. The 20 negative cancel the 20 positive, but you still have 5 left over, which give it a charge.
Okay. Thank you.
So in a normal atom that's not charged, number of protons equals number of electrons. But that can become imbalanced. So you remove electrons from the atom, it becomes charged because now you have more protons, more positive charge than negative charge in the atom. Moving on to isotopes. Isotopes are atoms with the same number of protons, but different numbers of neutrons. They behave the same way chemically. All that's different about them really is their mass. Neutrons add mass to the atom. They don't add charge. They don't add anything that causes them to change how they behave chemically. It just makes them change their mass.
Then what's the point of neutrons?
Neutrons help make it stable. So the ratio between neutrons and protons helps the atom stay stable. If you have too many neutrons or too few neutrons, the atom could fall apart. And so there's certain, plutonium, for example, uranium, there are certain atoms that are unstable in certain cases when they have too many neutrons or protons, and they're radioactive and they fall apart. The mass number is the number of neutrons and protons together. So we ignore electrons for mass. They're so small compared to protons and neutrons that compared to the electrons, basically it's like dust top of a scale. You know, if you were to weigh your book and add some dust particles, it wouldn't change your book's weight. And so that's compared to as how large the nucleus is compared to electrons. It's like a book compared to dust. So we can ignore the electron's mass because it's so small, it won't make a difference in the weight, and look just at the mass of the protons and the neutrons to get the mass of the atom. So for carbon, you can see that there are different isotopes. Normally, carbon has 6 protons, 6 neutrons, 6 electrons. So that's what this stands for, 6 protons, 6 neutrons, 6 electrons. So most carbon atoms, that's what they have. But they can have other combinations too. Some carbon atoms will have 7 neutrons or 8 neutrons. Now, every carbon atom, though, only has 6 protons. So the number of protons gives the identity of the atom. So 6 protons means it will always be carbon. If you add 1 more proton, it becomes a different atom. So you go from carbon to nitrogen. So going from 6 protons to 7 protons, you get nitrogen. But the number of neutrons can change in the atom, and it's still the same atom, just a different mass at that point.
So if you add neutrons, it's still stable, but if you take
Well,
them-
it can become unstable either way. So adding or subtracting neutrons, it can become unstable. It depends on how many you have. We'll talk more about it in 4.4 when you know it's unstable, when it's not.
So if it's small enough, it can stay stable if you add a bunch.
Yeah, smaller atoms are more likely to become stable or stay stable. Bigger ones become more unstable faster. But even for carbon, some are unstable too. Carbon-14 is not as stable as carbon-12. So carbon-14 does degrade over time to carbon-12. And you might have heard of carbon dating before. Have you heard about that in history class? So what do they do with carbon dating? Well, carbon over time naturally goes from carbon-14 to carbon-12, which means that you can get an idea of how old something is by looking at how many carbon-14 atoms you have versus carbon-12 atoms. It predictably ages over time, and it transfers from carbon-14 to carbon-12. And most things are carbon-based, right? Fossils, paper, plants, fabrics are all carbon-based. And so carbon dating is useful for artifacts about 5,000 years and younger. Once you get beyond 5,000 years, it's really not, and even 2,000 years can, even at that point, it can be unreliable. But generally, for a few thousand years, it's fairly reliable as far as knowing how old something is, but not always. The Shroud of Turin was carbon dated. Did you hear about this? See what the Shroud of Turin is? That Jesus was buried in a cloth where basically this three-dimensional image of his body was transmitted to this cloth. It's amazing. They can take it and use a computer to generate a three-dimensional image of his body perfectly from the Shroud of Turin. They don't know how this is made. I mean, of course, we believe it's a miracle, but for scientists who don't believe in this as being a miracle, they don't know how this happened. There's no pigment that they can point to explain how this could have happened. It seems like supernatural as far as they're concerned. I believe it is supernatural and a miracle, but they don't know, they can't explain this with science. But they took a part of this fabric and carbon dated, and they said, well, it's in 1500, 1300 AD. Well, they took it from a part that was fire damaged. So you have to be careful carbon dating, because if it's damaged in fire, that's going to skew the results. And that's what happened with the Shroud of Turin.
So the second picture, the one where it's like, I don't know, how do they know that it's six protons and then 8 neutrons?
How do they know that?
Yeah.
As far as looking at just the picture, or like just in.
Like it says carbon's 14 and then it shows those, like how
Mhm.
would you find?
Like these right here?
Yeah.
You have to just be told that.
How do scientists figure out how many protons are in an atom?
Nuclear imaging, they have machines that can use X-ray or centrifuges to determine the mass of the atoms. So carbon has several isotopes. Carbon 12. So the 12 represents the mass number. That's how many protons and neutrons together it has. So carbon 12, 6 plus 6 gives you 12. Carbon 14, 6 plus 8 gives you 14. So 6 protons plus 8 neutrons gives you 14. And that's how you get the number. So the last number on carbon 12, carbon 14 is the mass number.
So how do you know it's not 8 neutrons and 6 protons?
You mean how you know it's not 8 protons and 6 neutrons? Like the reverse of that? Because protons gives you the identity of the atom. And so if it's carbon, it's always 6 protons. If it's 8 protons, well, that's oxygen right here. So the top number on here tells you how many protons the atom has, and the protons tells you its identity. So this top number right here, you can write it like this, where you just write it as carbon 12, where the 12 is the mass number, or like this, where the 12 is a superscript, or like this, where you have the mass number and then the atomic number. So those are different ways you can write it. They all mean the same exact thing. They tell you the mass number 12, which means the protons and neutrons together add up to 12. Carbon 14, 6 plus 8 gives you 14. Also carbon 13, which I didn't show you in the picture, but carbon 13 would have 6 protons and 7 neutrons to equal 13.
But it also has to have 6 electrons.
Exactly. Yeah, if it's neutral, it will always have number of protons and electrons be the same. So yeah, that's a good point to bring up. In all of these isotopes, it's always 6 protons and 6 electrons. That does not change. One thing to talk about too, there's no normal isotope. You know, carbon 12, carbon 14, carbon 13, they're all the same thing. It's like using the word brothers or sisters. I mean, that's, you don't have like one standard sister and the rest are just secondary. They're all sisters, they're all brothers in a family, they're all related to each other. So isotopes are all kind of like that, where they're all related, they're all in one family. And so they're all carbon, just different masses of carbon. Let's not go through that right now. Okay, so I want to work on some questions for the rest of class today. Let me see, in your book, start on page 116. and start at number 12 and go on to the next page, go up to 17. So do 12 through 17, starting on page 116.
Can I send the like?
Yeah, that'd be great. Thank you.